So my presentation will be about in vitro bioassays. And I'm not sure how this is in America, but at least in Europe, when I started working on this about 10 years ago, the industry was really skeptical about bioassays because they only knew it from a huge scandal which was done in Europe. A lot of people were afraid of hormone-active substances leaching out of PD bottles because there was a study by a German university who detected quite a lot of estrogen activity, activity like the female sex hormone in mineral water, and they concluded, well, the only plausible source would be the PD bottle. In reality, nobody ever really tested the PD bottle, and this more or less brought me my job because this was then my topic to really, as one of the first people, really directly test the packaging with the in vitro bioassays. And actually, we were able to show that the in vitro, with these in vitro bioassays, that this estrogen activity, wherever it came from in the mineral water, was definitely not caused by the PD bottles. But this, so you could see there was maybe a bit of an unnecessary panic in this, on this hormone activity of PD bottles. But for me, it was not unnecessary because it got me my job. It got me very soon working on this topic in vitro bioassays of food packaging. And I hope that today I can show that actually this is not only causing troubles, but this actually might be helpful for the safety assessment. So you may ask, well, we've lived very well without bioassays for many years. Why do we now suddenly need bioassays? Well, at least in Europe, there was quite a change in the safety assessment. Traditionally, the safety assessment in Europe focused very much on what you're using for the production, therefore what you put inside the packaging, like what additives are you using, monomers, and then the safety assessment was, for these substances, you know what they are, or at least in a perfect world, you would know what is used for the packaging. We all know that this is not so easy in practice. And they are well toxicologically characterized, and you have certain thresholds. And if you're below them, you can say it's safe. If you're above them, then there's a risk. But it's not so easy when you are actually looking on what's really coming out of a packaging. So just to start and to be clear on this, if you know what you're looking for, I would never recommend a bioassay. A chemical analysis, as we've seen in the first lecture today, it's much more precise. It is also, honestly, a bit more reliable. So if you know what you're looking for target analysis, stick with the chemical analysis in any way. But nowadays it's getting a bit more complicated because very often we do not know what we're looking for, because now also in Europe, I think in the US it was always this way, the focus is not on what have I been using for the production of the packaging, but the focus is what is actually migrating out of the packaging into food. And of course, to a certain degree, we are talking of the same substances, because some substances that you're using for the production will also migrate out of the food. But here we also have this non-intentionally added substances, the so-called NIAs, substances that were never intentionally added, like degradation products, contaminants of the starting substances, or oligomers, some other byproducts of the polymerization process, for instance. And so far in Europe, more or less, these non-intentionally added substances were, let's say, ignored to a certain degree. But nowadays, at latest since 2016, there's really a law which definitely requires you also to evaluate the risk of non-intentionally added substances. More or less, you were always required because there was always a law stating that no harmful substances may leach out of the packaging. But now really it's really definitely mentioned you have to evaluate the risk of non-intentionally added substances. And this is quite difficult for European companies because very often it's technically not so easy to do so. Here, if you're hoping, now I'm presenting a very easy solution for non-intentionally added substances. Just say, I have the solution, there's a bioassay, it's either green and everything is fine, or it's red and you have a problem, then I really have to disappoint you, because you will still need the chemical analysis, as we've seen in the presentation, the first presentation today. You will still need this, but sometimes after this analysis, there will be still some open questions. And here, in vitro bioassays, as an additional tool, can be really helpful. I will try to explain this by an example. And this is not such a nice example as the ones that we've seen from Thomas. It was actually a new type of in this example, it was quite a new type of a biopolymer where we have not so much experience with interpreting what's migrating out of it. And in this case, we were not able to identify all these peaks such beautifully as we've seen it in Thomas' presentation, but actually of 51 peaks that we detected in total in a GCMS screening, there were 24 which we simply could not identify. And honestly, when I would show an HPLC result, there would be even a much higher fraction. So this is a problem that I think all laboratories working on non-intentionally added substances are facing quite often, that you simply don't know all these substances. And sometimes even if you can identify them, it's very difficult to get a pure chemical standard to really verify if this is really the substance that you're suspecting it is. The problem is, it's already very difficult for these 27 substances that were clearly identified, because here you very often have no toxicological data, but at least you have something to base your safety assessment on. But what do you do about this non-intentionally, this not identified substance? How can you say if a substance is safe if you don't even know what it is? Well, honestly, what we are doing at OFI, and I'm not very proud of it, is we're trying to get around it somehow with some statements where, like, no critical substances have been identified in the GCMS screening, which of course is true, but we always have to hope that there's nobody putting his finger here and say, how do you know that these 24 substances are not critical if you do not even know what they are? In Europe, this finger is not very often put on these unidentified peaks by the auditors or by the authorities, but now increasingly the big brand owners are asking. And we now often get requests by clients who said, okay, I was asked by one big brand owner, what are these substances? And it's really difficult to identify all these peaks. And I know examples where they spent really 20,000 euros in getting a better analytical method. The problem is you identified 10 additional, but at the same time you find 20 new peaks that you maybe are not able to identify. So I think it's very important that these libraries are getting better, but nevertheless, I think to be realistic, we will not be able in the near future to identify all of these substances. So there is also a need for some other approach that helps with the substances which are not identified. And in case that I forget later, I have to say this is really intended for not identified substances. So whatever I'm telling now about bioassays, it's not intended as a shortcut. If you have substance like I have critical substances identified, say let's test it with these OFI in vitro bioassays and hope it's negative, and then I can ignore that I found a critical substance. No, this is not the intention. But for these non-identified substances, we need some additional tool. So, on the other hand, if you look at it, there's good old Paracelsus telling you that dose makes the poison. And if you're looking at these low concentrations, and in Europe, we have a non-detect requirement of 10 ppb, so more or less you have to evaluate the safety of all peaks above a concentration of 10 microgram per kilogram in the food or food simulant. And at these low concentrations, if you look at typical poisons that you maybe know from some Agatha Christie or something like potassium cyanide or something, at these low concentrations, most of them are completely harmless. So I've asked for many people, what are we doing here? Are we have we lost the focus when we are catching each and every peak in the low ppb range? Can we not simply ignore this and say it doesn't matter? The problem is, and although I agree that sometimes maybe you could argue that the food packaging is the most healthiest part of the food in total, but nevertheless, I wouldn't say that you can ignore these substances just because of the concentration, because there are certain types of substances which can already be critical at these low concentrations. Most importantly, it's genotoxic substances. A substance, and even among these genotoxic substances, not all of them are critical at very low concentrations, but at least those really directly interact with the DNA and cause mutation. They can really be critical at very low concentrations. Actually, there's no real safe threshold. And in theory, even a single substance, if it would make all the way from the food packaging through the body to a certain tumor suppressor gene and cause a mutation there, then this might be the first step. But you wouldn't drop dead immediately. You wouldn't immediately get cancer. But it might be one of many steps that lead finally to the formation of cancer. Therefore, if you take it up every day, and the assumption, which is maybe a bit over-conservative, is that you take it up over the next 70 years every day, then there's a risk even if the concentration is very low. There's another substance group, and here it's not so clear, and the toxicologists are still discussing this very controversially, and I'm very happy that I'm more from the analytical side and don't have to make a statement whether bisphenol A or endocrine disruptors in general are critical or not, but definitely there are discussions ongoing if not endocrine disruptors are also substances that can already be critical at very low concentrations. And here bisphenol A, of course, is the best known example, but actually there are quite a lot of other substances in the food packaging area which can have more or less similar effects. We've seen today in the presentation of Thomas, for instance, nonylphenols or other degradation products of antioxidants can also be endocrine active. This does not mean that they are dangerous, but at least there is some insecurity in maybe they also be critical already at low concentrations. And let's face it, this is also about trust and public perception, because the consumers do not accept if there are some substances in the packaging that interfere with the hormone system. Even for bisphenol A, where FDA and EFSA say at these concentrations it's safe, we see that nevertheless companies are moving away from it simply because the consumers still are not convinced that it's really safe. So one thing that could be helpful with non-identified substances is the threshold of toxicological concern, and I think we will hear about this more in the next presentation, but nevertheless, just briefly, the concept behind this. This is more or less simple statistics. So what was done is take a lot of data from many different substances, and for all of these substances, there are some safe thresholds derived. And then just by simple statistics, a value was derived where you say, okay, based on this set of data, I can say below a certain concentration, even if I don't know what the substance is, there's a very low risk that it's actually harmful. The problem is, if you know absolutely nothing about a substance, you have to consider the worst case. And the worst case would be that the substance, this unknown peak, is a DNA-reactive genotoxic substance, something mutagenic. And then you would derive at a TTC of 0.15 microgram per day. So here you can say, okay, for all substances where the exposure is less than 0.15 microgram per day, I don't have to worry, even if I don't know what they are, they will not be critical. The problem is 0.15 microgram is practically nothing. This is usually below the detection limits. So if we have no further information, then this TTC concept helps us practically nothing. But if some substance groups can be excluded, and these are something like heavy metals. I would not recommend a bioassay here. I would rather recommend to go to Kiev or some other laboratories who are doing like ICP analysis or anything on the heavy metals, because here I simply don't see a reason why bioassays should be applied. There are some other substance groups which can relatively easily already with current techniques be excluded, but one substance group is really difficult, and this is the genotoxic substances. And here, actually, if you read the whole EFSA and WHO report, it's not even the whole range of genotoxic substances, but it's those that are really DNA reactive. Problem is, this is a very wide range of very different substances, and at the moment, there's no chemical analysis method where you really can exclude all of these substances without more or less having only positives, because there's some indication for a possible genotoxicity alert in every sample. So this is the main thing that has to be resolved, and one suggestion would be use in vitro bioassays that specifically detect if something is reacting with the DNA. For the endocrine disruptors, actually, at least in Europe, EFSA and WHO have done this recommendation for the threshold of toxicological concern. And at the moment, endocrine disruptors are not especially excluded, but I know that there are some discussions going on, and also we are also working on medical devices, and here endocrine disruptors are not even included in this worst case genotoxicity. So this is a bit of an insecurity, at least I would say at the moment in Europe. Maybe sooner or later they will be excluded as well. But if you can exclude genotoxic substances and exclude something else which is a bit more easy, then you could say it's a Kramer class 3 substance. I won't go into detail what this Kramer class 3 means, but more or less is if these groups are excluded, then you can again do these statistics by the TTC, but now you derive at a much higher level, and you can say if the daily exposure is less than 90 microgram, therefore a factor 600 higher, if it's less than 90 microgram, then you can assume that the risk is low. So this does not mean that you can apply this for known chemicals where you have toxicological data, but again, this is a very useful tool if you have no toxicological information on a substance. It's originally intended for known structures, so if you know what the substance is but you have no toxicological information, but recently the EFSA and WHO confirmed, it's a bit hidden in the 190 pages report, but they confirmed that in principle this can indeed also be applied for unidentified substances in a complex mixture. So the idea would be, if you can exclude that all these substances by somehow testing the mixture are consisting of DNA reactive genotoxic substances, and if you can also exclude some other groups, which is not so the focus of my presentation, then you could, for unidentified substances, say, okay, below a daily uptake, an estimated daily uptake of 90 microgram per day, you can assume that the risk is low. Whereas if you cannot exclude this, then you would, in Europe, have to apply at least with this 10 ppb non-detect requirement, or actually would have to go down to 0.15 microgram. So this idea approach sounds promising, and I have to be very honest here, this was not my idea. This idea, I think, was originally developed by Sander Koster at the TNO in the Netherlands, and he is now working for Nestlé. Therefore, this whole approach is very much pushed in Europe by Nestlé. This is also why suddenly everybody is so interested in the bioassays in Europe, because when the industry is thinking, okay, if Nestlé is working on this, maybe it makes sense to have a look on this. And also, this has already been published. The European Parliament has stressed that in vitro bioassays should be used, and there is a paper by ILSI, which is got a lot of attention in Europe, which also recommended that if you don't know, if you are not able to identify a substance, then you should apply in vitro bioassays. But the problem is, it's not very specific. More or less, it just suggests use genotoxicity testing, endocrine activity, and cytotoxicity, but it gives no details on what kind of methods, how do you do the sample preparation and everything. So what's currently being done is a lot of people are working with in vitro bioassays. There are really a lot of studies. All of them are very well conducted, I would say, but nevertheless, you cannot compare the results. And this is also difficult for the industry, because if you have 20 different methods, you can be sure that in one of these 20, more or less every sample will be positive. So it was agreed that it needs some better standardization. And here also ILSI is doing some work. There's an ILSI expert group. I'm also part of it, and it's chaired by Benoit Schilter from Nestlé. And here we are working on more specific recommendation on how bioassays could be used for the safety assessment of unidentified Myers. And in addition to this, because the ILSI expert group, this is just a literature review, so it's based on existing literature. And what we soon found out is, at the moment, there are still knowledge gaps in the literature, and so there's really some research work required. Therefore, in parallel, we at the OFI, together with the University of Applied Science in Vienna, are also working really in the laboratory on development and validation of in vitro bioassay methods. And so now I try to shortly explain how these in vitro bioassays work. What, in my opinion, is the most important test in this area is the Ames test, because this is a very well accepted test for the detection of DNA-reactive genotoxic substances, mutagenic substances. It works with bacteria, and it cannot detect all types of genotoxic substances. But at least in the threshold of toxicological concern, it's claimed that those genotoxic substances that are really critical at very low concentration, those are the substances that are directly interacting with the DNA, and they can also be detected with bacteria-based assays. So how does this work? You have a certain Salmonella bacteria strain, and this has a mutation on a certain gene, and therefore normally it would not be able to grow on a media without the amino acid histidine. However, if by coincidence there is another mutation that reverses the effect of the original mutation, then this bacteria could grow again. So what you would normally have is, of these really very many billions of bacteria, there will be maybe 10 or something who have this mutation just by coincidence. But if there's a mutagenic agent, something that is reacting with the DNA and causing mutation, then the likelihood that this reverse mutation will happen is much higher, and then you will see much more bacteria growing. And this is how you see if there's a DNA-reactive genotoxic substance in a sample. This test is very well established. It's actually one of the oldest genotoxicity tests. It's used for regulatory testing of pure substances for a very long time. The problem is it's not so easy to simply transfer this method and use it for food packaging, because normally you would need, let's say, 5 milligrams of a pure substance and dissolve it and test it here. So this was one of the work that we were doing. The problem is, if you're looking at the food packaging, then for a normal full Ames test, you would have to evaporate, let's say, 20 liters of a food simulant to really get the concentrations that you are sensitive enough. That's why we are working with a miniaturized version of the Ames test. It's not as well accepted as the full and normal Ames test on plates, but it still has a very good similarity, and at least in the pharmaceutical world, for impurities under certain circumstances, also these miniaturized versions would be possible. So more or less the same principle, but in a 384 well plate. Then there are other tests focused on endocrine activity. How do they work? More or less, they try to simulate how a hormone works in the human body. So how does, for instance, an estrogen work in the human body? It binds to an estrogen receptor. Therefore, the conformation of the receptor gets changed. This is very much simplified. And it can bind to a certain region on the DNA. And then a certain gene is activated. And this gene, maybe in the human body, triggers some typical response to an estrogen. Let's say, to have a more spectacular example for a teenage girl, it could be one gene that somehow triggers the growth of the breast. The problem is, even if these genes maybe have a huge effect in the human body, they are still very difficult to detect. Therefore, in these bioassays, when we are simulating this in a cancer cell, this gene is replaced by a very easily detectable firefly gene, which causes the light reaction of a firefly. Therefore, if substance binds to the estrogen receptor, activates a certain gene, then you can see a light reaction. And this is a very sensitive and very reliable test that really tells you if there's some substances that, like the female sex hormone or like the male sex hormone testosterone, depending on the test setup, bind to the receptor and therefore activate it. The advantage is, if you have, for instance, instead of bisphenol A, a bisphenol F, or some other bisphenols with the same properties that everyone is so afraid of, that they can bind to the receptor, you would still detect it, even though maybe with a chemical analysis you would miss this if your target analysis is just based on, let's say, bisphenol A, F, and S, and then this is some additional methyl group, you might miss this. Here it's really focused on the effect that acts like female sex hormone, for instance. So how does it work? How do we, I mean, these tests honestly are not so new and very similar actually to some of the tests that are in this EPA test battery, like Tox21 and everything. But what's actually not so easy is to take tests that are intended for pure substances and find a good procedure to also test the food packaging, because here the big difference is you actually have to detect low concentrations of a substance in a complex mixture. So what we are doing is, the migration is very close to what we already heard from Thomas. It's mostly based on European legislation. The only problem is at the moment, I will come to this on the next slide, that currently we are still very limited with the choice of solvents, and what the only solvent where we really have a validated method at the moment is 95% ethanol, because it's a volatile solvent. But except for this, it's more or less classical migration testing. Then we have to do a pre-concentration. The problem is these tests are actually worthless if we do not have very low detection levels, because we want to focus on substances that can already be critical at very low concentrations. So if we cannot detect them at these very low concentrations, then these tests would not be really helpful. So here we need a high concentration factor, and at the end, after concentrating and transferring to a bioassay compatible solvent like DMSO, we are doing the bioassays. So most important, and those are the bioassay, which is at the moment the one the ILSI expert group is focusing on, the Ames test for DNA reactive genotoxic substances, but we are also doing the endocrine activity testing. And we are also looking for cytotoxicity, which to a certain degree also is simply to see if because if the cells are dying, then you cannot expect them to produce this firefly enzymes. One of the big problems is, if you look on the broad range of genotoxic substances, then they have very different chemical properties. Some of them are very volatile, some of them are not volatile at all. Some of them are very hydrophilic, some of them are very hydrophobic. And it's not so easy to concentrate by a factor of at least 300 all these very different substances without losing a considerable fraction. At the moment, the only way where we really managed to get results that we were happy with, or more or less happy with, is an evaporation. Of course, the highly volatile substances you will lose, but it's unrealistic that you really catch all substances. But if you have an easily volatile solvent, such as 95% ethanol, then an evaporation, very, very carefully evaporate avoiding evaporating to dryness, adding DMSO as a keeper, actually gives you quite good results. But if you would, for instance, use 3% acetic acid as a simulant, then by evaporation you would already lose much too many of the more volatile substances. So here we are currently working on something like a two-step solid phase extraction method, but it's not yet finally validated, and I'm not showing results at the moment, maybe on later conferences. So here we have to think of, and I'm now showing results, that the migration actually is not very realistic. For once, we have 95% ethanol is a worst case food simulant. A worst case food simulant for a fatty food, but if you, let's say, have a lemonade in the packaging, then it's highly exaggerated. Also, we cannot use Tenax for dry food because it's estrogen active itself. So we have some limitations here, and the results that I'm now showing are therefore not really a realistic exposure estimation, but it's somewhere in between a migration and an extraction study. And I also, before I really go into the results, have to start with another disclaimer. These results are not really representative for the market. Most of the samples we got from companies who took part on our research project, and they have the chance to supply us with a certain amount of samples, and they get the results afterwards. So I think these results, they are biased in two ways. For once, those companies who took part on the project, our companies really take a lot of care on what's in their packaging, and really are investing a lot in trying to find out if there's something harmful. So I would guess that their packaging in general maybe contains less harmful substances than the packaging worldwide. On the other hand, there are many really big companies, and of course they are also paying a certain amount for having these analyzers. So they are, rather from the whole spectrum of many different packagings, they are choosing the packaging types where they are afraid that they most likely have an activity. Therefore, this is really a biased sample and not a representative sample. We have a cooperation with a food retailer who provides us with some empty packaging, so we try to get a bit of a more representative picture. But just to be on the safe side, this is not representative for the market. So what can we see? For the endocrine activity, here we have not can coatings included. Otherwise, we would, because we have quite a lot of can coating samples, and for bisphenol A or some other bisphenols, we get a really high fraction of estrogen activity. This is mostly plastic samples. And yeah, let's start with the Ames test. There is only one, or in the two samples were positive out of the 31 tested in the Ames test. And you would say, okay, this actually is something that really sounds critical if there are mutagenic substances in the food packaging. Maybe a bit reassuring is, in this case, we tested the printed outside, because the idea of the client was, let's test the printed outside, and if it's negative, I don't have to worry about set-off effects at all. So, but we tested them, and then it was mutagenic on the outside. And actually, even if it's only the outside, you cannot ignore this, because normally a packaging should not contain any mutagenic substances at all. We test, and this is a bit reassuring for me as a consumer, we tested the inside and it was negative. Nevertheless, I would not say ignore this result, because I will show on the next slide, we are not yet there with the detection limits where we should be. For the estrogen activity, what does this positive samples mean? Well, it means that there's something binding to the estrogen receptor. This could be bisphenol A as a well-known example. This could be some degradation products of antioxidants, certain like trisnonylphenol. And this could also be, for instance, some oligomers of polystyrene. Just based on the bioassays, we don't know. We just know that there was something binding to the estrogen receptor. And what's also important for me, we also don't know that this is necessarily harmful, because actually also in food there are substances binding to the estrogen receptor like phytohormones from the soybeans or something, and here it's rather connected with positive health effects. So what we can say from the bioassays alone is only there's something which binds to the estrogen receptor or androgen receptor and is therefore acting like a female sex hormone in this bioassays. We cannot say that it's harmful for humans. And actually, if you test food, then you get a lot of estrogen activity. So for positive results, it's a bit tricky for us because we can neither tell people it's safe, nor we can tell them it's dangerous. However, if we have a negative result, then you really see the power of these bioassays, because for a negative result, we can exclude quite a broad range of different substances which have a specific effect, like, for instance, binding to the estrogen receptor, no matter if this is maybe some newly invented bisphenol, which you do not yet know that it's also just the same estrogen activity as bisphenol A. So a negative result really lets you exclude a broad range of different substances. And a negative result is even worth more for the Ames test, because then with some additional data, you might be able to conclude that this is a Kramer class 3 substance, and this would mean that the risk is low if the daily uptake is less than 90 microgram per day instead of less than 0.15 microgram per day. One thing which has to be considered here is, of course, for chemical analysis, everybody understands that you have to fulfill certain detection limits. And I think Thomas, for instance, would never have thought of that he doesn't present a report without detection limits. For in vitro bioassays, this concept is not so well known for the toxicologists because they mostly test pure substances. And if I test a pure substance, I don't really mind at which concentration it can be detected. Therefore, we see a lot of studies done on in vitro bioassays also with packaging, but many of them never evaluated at which detection limits it really can be detected. We did it for some substances. We evaluated the detection limits, and for the Ames test you can see that if you have quite highly active genotoxic substances like benzapyrene or 4-nitroquinoline, then you really have quite low detection limits, which are below this 10 ppb level, but still quite above the 0.15 microgram per kilo food from any food product. So even for these highly active substances, we are not yet really there where we could detect them at the concentration we would like to. But I would say, okay, for chemical analysis, there's also this non-detect requirement by the European Union of 10 ppb, which is not for mutagenic substances, but for non-intentionally substances, more or less the legislation recognizes you cannot have this low detection limits because it's technically not feasible. The problem is, for more realistic substances, what is really used in food packaging are mostly substances which are not strongly mutagenic. And we have here also the example of the batch, the bisphenol A diglycidyl ether, which is also a slightly mutagenic substance in the Ames test. And here you can see that we have a much, much higher limit of detection in the range of 1,000 microgram per liter. Why is this? Because in the Ames test, substances which are not so strongly mutagenic are also need higher concentration to get the same effect on the bacteria, because they are at low concentration and they are not mutagenic enough. The good thing is that there is at least some correlation that these substances which can be detected at higher concentration in the Ames test are in general also less mutagenic in humans. And for the example of batch, the detection limit would be, the legal migration limit in Europe would be even higher than this 1 milligram. And here you have one example where we cannot detect the substance at all, but this is not a direct DNA reactive genotoxic substances. And these substances, which for instance work by some chromosomal damage, they are actually covered by Kramer class 3. So I'm coming to my last slide, where I'm also showing an example for what bioassays can also be applied. And this is at the same time I see it as a big chance, and also honestly it worries me. This is a so-called safety by design approach, and it was, for instance, used by Nestlé to choose substitutes for bisphenol A, because they don't want to go from bisphenol A to another coating which just has the same problems. So they say, I don't just say it has to be free of bisphenol A, but just in general no endocrine activity, certain different hormone activity tests, genotoxicity, cytotoxicity, and then you can say, okay, if there's no technical reason speaking against sample 2, 4, 5, I rather choose them than maybe these samples which show some problems. But one thing that I have to stress is that these positive samples are not necessarily harmful. Just because there's a positive response in the bioassay, it does not mean that you certainly grow breasts or die of cancer. It's just an indication for a possible effect. And this last column here, the sample 6, which looks very scary, is actually a coffee from a coffee machine at OFI. I'm still drinking a lot of coffee, so.
Sorry, one question I have is for BPA.
Please go to the microphone. Let's just put it back, he's almost done. And we'll just take the question.
Okay, I remember the question. So you have to be careful, because if someone would have done this safety by design approach and have decided coffee should not be longer sold, then I would be always tired the whole afternoon. So it's a very useful tool, but one has to be careful. And when this is presented by Nestlé, they exchange this red by green because they want to let it be a bit less scary. On the other hand, I'm aware that I think nevertheless, if this slide is presented by Nestlé for the industry, it's even more scary than when I present it, no matter on what colors they are using. And yeah, what I also want to thank a lot is the University of Applied Sciences, who are working with us together on the project, and more or less half of the results which I'm presenting now have been actually performed by the university. I also want to thank the ILSI for letting me take part in this expert group, which is really great for the standardization, BDS for supplying the great bioassays, and also the Nestle Research Center, because they are actually sharing all their protocols. They're also doing a lot of work for in vitro bioassays testing, and it's good that we here not working in parallel and completely different topics, but that we have the ability to share protocols.